Well, how did you do? Let's see how you do this. We know that the density, rho, is in kilograms per meter cubed. I tell you that. G is an acceleration. We've already seen that's in meters per second squared. H is a height, so that's in meters. There's some cancellation of some of the meters, and we end up with kilograms per meter second squared. And so the correct answer is D. Now, note that B and C are both correct SI units for pressure, but they're not in base units. And A, PSI, is correct units for pressure, but it's not SI. There's one more important rule for dimensions in equations, and it has to do with transcendental functions. Now, you might not know what a transcendental function is, but you've certainly seen lots of examples of them. The trig functions and the exponential and log are all transcendental functions. I wish we had time to go into what that means, but I'll have to leave that for your calculus courses. In any case, the rule is that the output of a transcendental function is dimensionless, and the argument, in other words, the input of the transcendental function, must also be dimensionless. So let's look at an example of that from Phys 1204. This is the current as a function of time in a type of circuit that we'll see. So this quantity I is a current. And we know that this exponential must be dimensionless, and so I naught must also be a current. We also know that the argument of the exponential must be dimensionless. T is a time, and so for that argument to be dimensionless, this quantity RC must also be a time. Now let's move on to significant figures, and I'm going to start by making a claim. I claim that my age is 1.451649642075141191 times 10 to the 9 seconds. Whew. My question is, do you believe me? Well, aside from wondering what sort of nut would give you their age in seconds, you might sensibly convert this to years and find that it's about 46 years, which seems plausible. But there's still something very wrong with this claim. If you count digit, the ones place is right here. All the digits past that are smaller and smaller fractions of a second. So in fact, the last digit represents nanoseconds. I've given you my age to the nanosecond. Do you believe I know my age to the nanosecond? There's a birth record in Ottawa, which has my birth date on it, but I doubt it's accurate even to the second, certainly not to the nearest nanosecond. And so I've given you a whole lot of digits that are not significant figures. They are digits that I have no way of knowing. That's all a significant figure is. It's a digit that we actually know. A caution, which I'll illustrate with some examples, is that zeros are a little complicated. Some zeros are significant figures, but others are what are called placeholder zeros, which just tell you the order of magnitude of the other digits. Look at this first number that I've written, 0.03501 seconds. I'm going to tell you it has 5 digits after the decimal place. We'll just count them. And there are 6 digits written down because there's the 0 before the decimal place. But it only has 4 significant figures. Those first zeros are not significant figures. They're placeholder zeros. They're there to tell you that that first digit, the 3, is in the 100ths of a second place. So they're establishing the order of magnitude. They're not telling us anything about what digits we actually know. And so this is the same as writing 3.501 times 10 to the negative 2 seconds. And if you write it that way, it's clearer that it has 4 significant figures. Here's another example, this 862,000 kilometers. So the 8, 6, and 2 are certainly sig figs. What about the zeros? Are those placeholder zeros? Well, we don't actually know unless we did the measurement. If we know that we actually measured to the nearest kilometer, and it just happened to come out to a reasonably round number, 862,000, then those are significant figures, right out to the last zero. But if we don't actually know it, if we only measured to the nearest 1,000 kilometers, then those are just placeholder zeros. So this is ambiguous, and you shouldn't write it this way. You should write it using scientific notation, and now you can make clear, on the one hand, if you only know the 8, 6, and 2, then only write them. But if you in fact know those other trailing zeros, you can write them in, and they are then clearly sig figs. What we are talking about here is precision. I want to highlight some of the issues that come up with precision in measurements, and so I'm going to give a couple of examples. Suppose we're measuring this object with a ruler. We need to know where the right end of the object is in relation to the scale. Well, we can just read the scale. It's closest to the 6.1 centimeter mark, but of course that means anything between 6.05 and 6.15 is going to get read as 6.1 if we just measure to the closest mark. So doing that, we've achieved two significant figures, or precision of plus or minus 0.05 centimeters. But we can do better than that. If you look very closely, you can see it's a little past the 6.1 mark, but less than halfway to the 6.2 mark. And so we could estimate that it's about 6.14. Now we've got three significant figures, and we're perhaps approaching a precision of plus or minus 0.01 centimeters, depending on the reliability of that estimate. Maybe it's closer to plus or minus 0.02 centimeters. What about digital calipers? They report a value, in this case anything between 0.565 and 0.575 would have been reported as 0.57, and there's no scale we can look at more closely, so that's the best we can do. So we've got four significant figures, or plus or minus 0.005 millimeters. Maybe, because there are other factors. The surfaces could have grit on them, the calipers might not have been well aligned, and so in fact that 0.005 millimeters is a best case scenario. And now I hope you're getting worried, because I'm using a lot of weasel words like best case scenario, or the precision can approach a certain value, and you ought to be wondering, what's the actual precision? The quick answer is that one measurement doesn't tell us the actual precision. The longer answer is that Lecture 3 is going to be all about how we use the statistics on a set of measurements to estimate the precision. Let's take a moment to check your understanding. So if you're in the course and if you're accessing these videos through Moodle, this video is about to end, and Moodle will ask you this question before sending you on to the next part of this video lecture. If you're not in my course, then I suggest you should still come up with an answer to this before you go on. So let's say your friend runs around a track, and you use a stopwatch to time them. And like most stopwatches, this one can be read to the nearest hundredth of a second. So naively, we'd expect that the uncertainty in the timing is half of that, or about 5,000ths of a second. So do you believe that your measurement of their lap time is this precise, to plus or minus 0.005 seconds? So have a look at the answers and come up with your answer, and then go on to the next part of this video lecture.